Hello everyone, in this video I will be solving two questions about advanced location problems. The first question is about the two-stage transportation model where products move from suppliers to plants and then plants to customers. The second question is about set covering, where we try to cover all demand points with the most cost-effective facility choices. So in this presentation we will see two different optimization perspectives. One focuses on shipping flow and total transportation cost, while other focuses on coverage and efficient selection. Let's begin with the first question. A company operates two suppliers, two plants, and two customers, so the movements of goods happens in two steps. First, products are shipped from suppliers to plants, and then they are shipped from plants to customers. We are given the available supply at each supplier, the capacity of each plant, the demand of each customer, and also the inbound and outbound costs per unit. The goal is to formulate the linear programming model and then find the minimum cost solution. So this is not just a basic transportation table, it is a network problem with multiple levels, and that means we have to satisfy all parts of the system at the same time. To model the system properly, we first need to define variables and objective function. The first thing we do is define the decision variables. The variable xij represents the amount shipped from supplier I to plant J. The variables yjk represents the amount shipped from plant J to customer K. So the x variables describe the first stage of network and the y variables describe the second stage. Then we write the objective function, which is to minimize total shipping cost. The first part of the objective includes inbound costs from suppliers to plants, and the second part includes outbound costs from plants to customers. What is important here is that everything is linear, each variable appears at a unit cost, and the total cost is simply the sum of all root costs. So this is a standard linear programming objective. First, we have supply constraints, which mean that each supplier cannot ship more than the amount it has available. Second, we have plant capacity constraints, which ensure that the total inflow to each plant does not exceed that plant's processing or handling capacity. Third, we have demand constraints, meaning that the customers must receive enough product to meet their demand. And finally, we have flow balance constraints at each plant. This is a very important part of the model. It means that whatever enters a plant must also leave that plant. In other words, the inflow to a plant must equal to the outflow from that plant. Together, these constraints make the model realistic because they connect all parts of the network instead of treating routes independently. Now that the full model is written, we can interpret the solution strategy and the final shipment plan. The basic idea is to prefer the cheapest routes possible. For inbound flow, the cheapest route is from supplier 2 to plant 2, with a cost of $3 per unit. For outbound flow, the cheapest route is from plant 2 to customer 2, with a cost of $2 per unit. Based on that logic, the solution sends all 60 units from supplier 2 to plant 2. The supplier 1 mainly fills plant 1 and sends the remaining 10 units to plant 2. On the outbound side, plant 1 serves customer 1 fully and sends the remaining amount to customer 2, while plant 2 covers the remaining demand of customer 2. After calculating inbound and outbound costs separately, the minimum total cost becomes $910. So the key idea in this question is that the cheapest solution is not decided route by route alone. It must also satisfy supply, plant capacity, and demand and balance conditions across the whole network. That completes the first problem. Now let's move on to different kind of optimization problem where the focus is not flow but coverage. In this problem, a city wants to place fire stations so that 5 neighborhoods are all covered. There are 4 candidate sites available and each site has both a cost and specific coverage pattern. So unlike the previous question, we are not deciding shipment quantities. Instead, we are deciding which sites to open. The method used is a greedy heuristic based on the minimum cost per coverage ratio. That means at each step we select the site that gives the best cost efficiency relative to the number of currently uncovered neighborhoods it can cover. This method is fast and practical, especially for larger problems, even though it does not always guarantee the absolute optimal solution. To start with the heuristic, we first compute the ratio for every single candidate site. In this part, we have to calculate the coverage contribution of each candidate site from scratch. For each site, we divide its cost by the number of neighborhoods it covers. This gives the cost per coverage ratio. The lower this ratio is, the more attractive the site is in the greedy heuristic. From the table, site F3 and site F4 both have the ratio, which is 200, so there's a tie. The slide breaks the tie by selecting F3 first. Once F3 is selected, neighborhoods N2, N3, and N5 become covered. That means only N1 and N4 remain uncovered. So after the first step, the problem becomes smaller and more focused. Now that some neighborhoods are already covered, let's compute the ratios using only the uncovered ones. At this point, the uncovered neighbors are N1 and N4, so now we only count how many of these remaining neighborhoods each site can still cover. That changes the ratios. For example, a site that used to cover 3 neighborhoods may now only help with the one uncovered neighborhood, so its ratio becomes worse. After recomputing the ratios, F2 and F4 are tied with the same ratio. However, F2 is chosen because it covers both remaining neighborhoods at once, while F4 only covers one. So selecting F2 immediately covers all neighborhoods and the algorithm stops. This shows an important feature of greedy logic. At each step, we use the current situation, not the original one. With all neighborhoods covered, we can now summarize the final solution and total cost. The selected sites are F3 and F2. F3 covers neighborhoods N2, N3, and N5, while F2 covers N1, N3, and N4. Together, these two sites cover all 5 neighborhoods. The total cost is $1,400,000 or $1.4 million. The slide also points out something very important. This solution is feasible and fast, but it may not be globally optimal. In other words, the greedy heuristic gives a good practical solution, but another combination could possibly have a lower total cost. So the main lesson here is that heuristics are valuable because they are simple and efficient, especially in larger coverage problems. Finally, let's close the presentation with the sum. These two questions represent two different but important optimization ideas in facility design and location. In the first question, we model a two-stage transportation system. The key challenge was to coordinate supply, plant capacity, customer demand, and flow balance while minimizing total shipping cost. In the second question, we solved the set covering problem using a greedy heuristic. There, the main goal was to choose facility locations that cover all demand points with good cost efficiency. Even though the both questions are of the same topic, they require different ways of thinking. One is about continuous product flow through a network, and the other is about discrete site selection for service coverage. Thank you for listening.